Hello and welcome to anyone who's just showing up in this evening's CNCF webinar. We're going to give it 2 or 3 minutes to let everyone filter in, and then we'll get started. Thank you. Just another reminder for those who are just turning up, we're going to start in 2 to 3 minutes just to let everybody join the webinar. I see people are still joining. If you're wondering why it's silent right now, we're giving those who are a little bit late a couple of minutes to join us. I think at about 4 minutes past the hour, we will get started. In the meantime, if you're kicking your heels, I would encourage you to check out the previous webinars on the YouTube playlist via the link that I just shared in the chat, or you can go ahead now and sign up for the next webinar we're going to have, which is an introduction to cloud native storage, and that's the second link that I just shared in the chat. Okay, it looks like the numbers are starting to equalize now, so I'm going to get started. Welcome to this, the 5th or 6th, I can't remember anymore, CNCF webinar. So as I just mentioned to most of the people in the chat, but perhaps a few just turned up at the last minute, I put 2 links in the chat. One is a link to the YouTube playlist that we have for all previous CNCF webinars. They're getting huge numbers of hits, so I would advise you to go and take a look at those. And also the second link that I put in there was the link to sign up for the next webinar in this series, which is an introduction to cloud native storage. Now, it's one of the webinars we've done with a whole host of presenters, so I'm not going to list them all, but you can find all the information there on the CNCF website, and that will take you through to a Zoom link, which will allow you to sign up. Now, today we have Ranga, co-founder of Avi Networks. Over the last 15 years prior to co-founding Avi Networks, Ranga has been an architect and developer of several high-performance distributed operating systems, as well as a networking and storage data center products. Today, Ranga is going to be telling us about cloud-native traffic management, and I can't wait to get started. But before we do that, a couple of house rules. Any of you who have been in the earlier webinars will know that we used to wait until the end to take questions, but we thought that just got a little bit boring, so we're doing it different these days. You can use either the Q&A window or the chat window to ask questions during the webinar. And as Ranga's going, I will take those questions and interrupt him at opportune moments to ask your questions to him. Ranga, are you ready to go?
Yes, Mark, I'm here. Can you hear me?
Then it doesn't really work online, but a big round of applause for Ranga, please.
Hey, Mark. Hey, guys. Thanks for being here today. As Mark said, we're going to cover traffic management in a cloud-native cluster today. My name is Ranga, and I'm a co-founder and CTO at Avi Networks. And for the past 4 years, I've been exclusively focusing on traffic management and how to do that effectively at scale in a way that you can actually deploy in production and keep applications running. So that's what I'm hoping to share today with all of you. So first, we will start by just talking about what exactly is traffic management. We will peel back the onion a little bit on the anatomy of a request as it comes into a compute cluster that's running your applications. And then we will dwell deeper into things like scale, availability, security, and so on and so forth. A recent survey at KubeCon in Berlin wanted to list out what are the top concerns in deploying and taking a cloud-native compute cluster to production. Not surprisingly, some of the top concerns were around networking, security, logging, storage, and then the complexity of all of it, and so on and so forth. And this is not surprising because all of these are complex topics, and what works in a POC, usually there's a lot of work and heavy lifting that needs to be done from take it to that into a fully production-ready system and a cluster. To start with, user accesses an application, and this is where everything begins. And this is the purpose of the cluster and the applications, of course, that we are deploying on the cluster. So first thing the user does is he or she does a request. Through that, he or she refers to the application by name, www.facebook.com. And this request is served by a DNS server that's usually sitting somewhere in the internet. And it returns what is known as an A record or an IP address that matches the name of the requested domain. And this IP address can be from one of many locations across the world. The larger an application is like Facebook or Amazon, then they are globally distributed. And we will talk about that in a little bit. But at this point, the IP address that's returned may be from a variety of locations. Regardless, the user is returned an IP address, and he or she then actually connects to the service. And as part of this connection, which is usually over TCP, a connection is established. And the first thing that happens is that the request, which is usually encrypted with SSL or TLS, it's a HTTPS request, is terminated. And this is usually done on the front end. And once the request is terminated, then there is a function called as a layer 7 routing that actually directs this request to a given application. And this is usually done based on some portion of the URL in the request. And note that this is different from traditional layer 3 routing because this happens at the application level based on the URL that the user is trying to access. In this specific case, let's go ahead and assume that this request is routed to an application called Photos. Now, once the request is routed, it's actually sent to one of several instances of applications. Why are there different instances? For a simple reason that one instance may not be sufficient to service all the requests. Also, if one instance fails, you need backup instances. So usually there are multiple instances of applications or servers that provide this service. And the device that actually performs all of this, we'll talk about that in a little bit, is called a load balancer. Now, once the request actually hits one of the instances of the application, it doesn't stop there. the request may need access to other services that run within the cluster. So some surveys of traffic patterns clearly have shown that about 20% of traffic is actually ingress traffic from outside the cluster by users. The remaining 80% is just intra-cluster traffic that just remains within the cluster itself. And these are usually applications or services accessing other services, which in turn access other services, and so on and so forth. Now, the first function that mapped the user's request to a domain name to an IP address, it's commonly called service discovery, and DNS is one of the most common forms, functions that provide service discovery. The second set of functions, including SSL TLS termination, and the actual device that performs routing, as well as the device that directs the request to a specific instance of an application, is performed by devices called load balancers or reverse proxies or application device controllers. That's a fancy term. Now, fast forward a little bit, and let's assume that the application is very successful, which is what we all want, right? We want to develop an application, we want it to be very successful. That means there are more users who are accessing the application. So the 101 of how users access an application is now gone into a second level of how do I make this application scale better? How do I make it perform better? Is that all of it? No. So more users come in, but you also want to develop more features and functions for the applications. You want to fix bugs. You want to be able to roll out newer versions of the applications. When you roll out a newer version of the application, you definitely don't want to see glitches for users. Almost all applications are globally deployed these days. They need to be available 7/24. So when you roll out a new version of application, you want it to go through, of course, a level of testing using your CI/CD pipeline. After that, you want it to be deployed in a production cluster without disrupting existing applications. Sometimes you also want to be able to test that the new version works fine for a small fraction of users before you deploy it to rest. So the other side of this is that you usually don't have just one cluster, right? You have your production cluster, you have a development cluster, and you may have an integration and test cluster. And depending on the number of developers, depending on the number of application instances that are being developed at any time, there can be a lot of churn in your cluster. This includes things like newer versions of applications being created, existing versions being scaled down, and so on. So the control plane of the cluster needs to keep up with this level of churn that depends on how many applications there are and how many developers there are, which can be quite substantial. So there are two dimensions that you need to keep in mind when your application starts becoming popular. One is how many users are accessing the application, which typically depends on which drives traffic pattern and load, and also how many developers are developing these applications and how often are they actually churning in the system. Which brings us to the next topic on how to scale your application. So as more users start coming in, the first function that sort of starts becoming the bottleneck is the SSL TLS termination. This is typically a CPU-intensive task. And if you don't have enough CPU resources dedicated for this, this can become the bottleneck. There are a variety of techniques for improving the performance of this, some of which include scaling out by deploying multiple instances of the device that performs this function. But regardless of that, you need to make sure that this function and layer scales and is able to perform adequately when the number of users and sessions starts growing. Once you have scaled out this layer, then the next layer that becomes a bottleneck is the actual number of instances that provide the application. Again, you need to be able to increase or decrease elastically the number of instances behind an application. You can do this based on a variety of techniques. It can be resource-based, where you're monitoring things like CPU utilization, memory utilization, and so on and so forth. It can also be performance-based, where you're monitoring things like latency of requests and the load on these instances. And if you see the latency starting to go up, if you see the load beginning to go up, you increase capacity by creating more instances. On the opposite direction, when the actual load goes down, you also want to decrease the number of instances. And you want to be careful when doing that, so you don't knock out instances that still have active sessions or active connections on them. So you need to have mechanisms by which you slowly drain these instances, and once they are fully drained, then take those instances offline. Okay, so those are some techniques you can use to scale different functions in this layer. So great, I have scaled my cluster. I have, I'm providing great performance. It's elastic. Is that all? No. So once you have deployed it and it's scaled and it's running fine, the next thing you need to worry about is availability. So this includes availability within a cluster. It also includes availability across clusters. So if one of the instances here, for example, instance 1 goes down, then there are other instances to cover for it. So requests still continue to work, the service is still up because it's actually provided by other instances that are running within the cluster. But what happens if the entire cluster goes down? Let's say it's an availability zone, or it's a region that goes down, or a data center that goes down. So, and this is a mission critical application for which you need global availability. So you need to deploy these applications across availability zones, across regions. And that's where the initial service discovery came in handy, because when a user requested the FQDN at the DNS service, the DNS service, or the service discovery, can decide whether it wants to direct the user to either data center on the left or to the data center on the right. And this decision can be made depending on a variety of policies. It can be made depending on the availability of the regions or the clusters. If one is unavailable for maintenance, or it's down for some reason, then all traffic can be sent to the other one. It can also be made depending on the proximity of the user. For example, if the user is closer to the cluster on the left, then all such users are directed to the cluster on the left. It can also be performed based on load. For example, if the cluster on the left is overloaded, then new users can be directed to the cluster on the right. Regardless of that, the service discovery mechanism is critical in directing users to the appropriate region and data center. And having your application deployed, especially the most mission critical ones, deployed across multiple AZs or multiple regions is very critical for the availability of your application. Great. So now you have been able to deploy your application. It's working fine. You have scaled it to users and your developers. You also deployed it across regions and data centers. You have made it available. Is that all? No. So the next aspect that you need to worry about is that there are always hackers trying to get into your application, right? So you have a variety of threats that you need to be aware of and you need to address. So the first thing, of course, is authentication and authorization. So you need to authenticate users. You need to sometimes apply policies based on their roles and their tenancy and so on and so forth. You also need to not allow unauthenticated users, ones perhaps with a bad intent, to access accounts. The other aspect of it is if it's a public-facing application, then you always have a risk of being hit with some kind of a denial of service attack. So if you have your application being hit with something like that, then you need to have a mitigation, detection and mitigation strategy in place to be able to deal with it. And the other thing that you need to be aware of and keep in mind is that you also need to be able to protect your application from attacks at layer 7 level. So the type of functions that provide that is called as a WAF, or a web application firewall, which detects and blocks threats at the layer 7 level. Now, if the worst does happen and the data center gets breached, then you also need to make sure that you're able to protect your most critical assets. In this case, for example, your database, and techniques like microsegmentation that provide policies on which set of containers or services are allowed to talk to which other set of containers or services. So you need to have microsegmentation policies in place so that just authenticated users and tenants are allowed to talk to each other. Right. So these are some security devices and measures that you need to have in place in such a way that you are able to protect your application from external threats. And in the worst case, if you get breached, then you're able to protect your application from within the cluster as well.
Ranga, would this be a good time to take a couple of questions?
Sure. Yes, please. Go ahead.
So we have we've got two in. Quite a general question from Ariel. How does this situation change with cloud native applications as opposed to what typically referred to as legacy applications in your container cluster?
Sure. So the big difference between cloud native and legacy applications is that legacy applications are often monolithic. So they are big instances of applications that are running in their cluster, and they don't change very often. So the set of techniques that you use to provide these services, the fundamental techniques are still the same, except that the cloud native applications are more decomposed as smaller set of services. So the requirement for automation is a lot more for cloud native services. And that is built in with cloud native cluster management solutions. So cloud native microservices require a lot more automation, whereas traditional applications have been built with sort of a more monolithic and then slow moving manual change control policies. That's sort of the distinction between those two.
Thanks, Ranga. I hope that answers your question, Ariel. And if it doesn't, please drop a follow-up back in the chat, and I'll ask Ranga at an opportune moment. Second question we had coming through from Dan Lamotte. He says, how do most companies do rolling updates of their load balancers at scale? And then in parentheses, where users terminate their TCP connections. And then he says, i.e. updating DNS records and wait for TTL or something else.
Yeah, that's a good question. So um, load balancers themselves are usually deployed as highly available pairs. So when you want to upgrade your load balancers themselves, there are a couple of ways you can do this. One is what you mentioned, which is you can point your DNS to a new IP address of a load balancer that you're not planning to upgrade. Wait for the existing TTLs to expire. So that way you're directing all the traffic to the load balancer you're not planning to upgrade. Upgrade the load balancer that should not be taking any traffic. And then do the opposite, which is flip your DNS back to the one that just got upgraded. Wait for a TTL period of time, and then upgrade the other load balancer. So that's one way you can do it. The other way you can also do it is you can do connection mirroring. So every TCP connection is actually mirrored to a load balancer, and so when that happens, then even if the load balancer goes down, then the traffic to the other load balancer can still be preserved because it mirrors connections. There's also an intermediate way you can do this, where you can actually move the virtual IP address to another load balancer. It starts responding to the virtual IP address, and when you do that, you all the new connections go to that load balancer. The existing connections, you wait until all of them drain. Usually these are short-lived connections. And then you upgrade this load balancer, and then you move all the WIPs back. So you're sort of migrating WIPs around. So the distinction between techniques 2 and 3 is that in technique 2, if you have really long running connection, then you have to mirror the TCP connections. In technique 3, which fit in very well with modern HTTP connections, you don't have to do TCP connection mirroring, which is quite expensive.
Thanks, Ranga. And Ariel, and Dan, if that didn't ask you a question, again, you can ask a follow-up. In the meantime, Ariel did ask a follow-up to the original question, and he said, are these functions then specific to container orchestration systems? I guess the question would also be, how does it change when you're using something like Kubernetes, Mesos, etc.?
Yeah, that's a great question. In fact, all these functions and techniques are actually common across almost all the major container orchestration systems, including Kubernetes and Mesos and Docker Swarm and so on and so forth. So the functions are all needed. The techniques are all needed. What, of course, varies is the details on how these are implemented. However, most of these are actually provided at the infrastructure layer by the orchestration systems. So these are somewhat hidden from the users of these clusters, from the developers. But if you are an infrastructure provider, either trying it out for the first time, or you have it running and you want to scale it out, then you need to be aware of these techniques and also how they actually work in these container systems.
Thanks, Ranga. That's all the questions for now, so you can you're free to continue to the next slide.
Sure, appreciate it. Thank you. So coming back to security, so there are a variety of threats that you need to be aware of and functions that you need to deploy to protect your application from outside attacks, as well as when a breach happens. Let's walk through. So your application's up, it's scaled well, it's available, and it's secure. Each of which is not very easy to do, but let's assume that you have done all these things. Is that all is needed? Not really. So you also want to know how your application is performing. So some aspects of that are about things like what latency latencycy are your users seeing. So are a percentage of them seeing errors, or are the percentage of them seeing higher latency or having performance issues? When you are being attacked, you also need to know what kind of attack was it, who did it, and also if something was really breached or not. So last but not the least, you need a lot of the ability to monitor what's happening in your cluster, see what is happening with respect to performance, with respect to security threats, and so on and so forth in your cluster. So you need a good monitoring system that provides insights into performance, infrastructure, any errors, configuration, audit trail, security threats, what attacks were prevented, what attacks were led through, and so on and so forth. So this is in addition to any level of application logging that you may need to actually troubleshoot your application level problems. These are more infrastructure monitoring and infrastructure visibility that you need to actually deploy your cluster in production. Okay, so so to round out, you need traffic management includes both ingress traffic that comes with a cluster as well as intra-cluster traffic. And you need a robust service discovery DNS mechanism, both for resolving names to IP as well as to actually direct traffic to the appropriate cluster based on availability, load, and performance requirements. You need reverse proxy or load balancing to do things like TLS termination, layer 7 routing, load balancing, things like circuit breakers, and so on and so forth. You need a good security implementation that includes microsegmentation, web application firewalling, authentication, auditing, and logging to make sure your application is secure. You need a system that provides good visibility into what is happening in your cluster and allows you to monitor and combines that with an alerting system. So if something does go wrong, you become aware of that. And last but not the least, you also need to plan your availability strategy on if an instance fails, a single instance fails versus if your entire cluster fails or region fails, and so on and so forth. And last but not the least, all these services can and should be implemented, integrated native into your compute, into your cluster. So the more integrated these services are in your cluster as part of the infrastructure layer, then the better they will work. The easier it will be to port them across different clusters, or when you're moving from data center to an instance of a public cloud. So that's coupled with automation for providing all these functions. That's a key requirement for successfully deploying the services and making sure that they run well in production. Okay. And this is my contact information. Of course, feel free to reach out to me at any time if you have any questions about any of these topics. I'll definitely discuss this. Happy to talk to you.
Ranga, thank you so much for the enlightening talk. We've got one more question coming through the chat, and I've also got one of my own. It's one of the privileges of hosting these things. They get to ask all the questions that I've been storing up for a while. Swana asks, as a follow-up to Ariel's previous question, how does this change if I have my cluster split across, say, public cloud, like, for example, GCP, and then on-prem? And will there be any functions that will need to be added or kept in mind or modified?
Good question. All these functions are definitely needed. The only differences will be Some of them are natively provided by the cloud provider. For example, a DNS service. AWS provides Route 53 as a DNS service. So does other major cloud providers like Azure and GCP and so on. So when you run natively in the public cloud, then you have a choice of using that cloud provider's infrastructure service like DNS. When you are running in your own data center, then you have to deploy a DNS service of your own, and you have a variety of choices that you can choose from. So that's sort of the service provider for each function can vary depending on where the service is deployed. But other than that, all the functions are the same, the techniques are the same, and you need to follow the guiding principles for deploying it, regardless of where you deploy.
Thanks, Ranga. My follow-up question to that was, you touched very briefly on the idea of what would now be called a service mesh.
Yes.
Linkerd is one of the most recent hosted projects in CNCF, and I'm wondering, what other things should be? I mean, previously I think people were used to maybe sticking Nginx in front of a few things and dealing with it that way. Now you have a service mesh that does a bunch of stuff for you, which is certainly an advantage. Are there perhaps things that we need to look out for when moving to that more, handing things off through a proxy kind of idea?
Sure. So a service mesh, the idea of a service mesh that provides a variety of these functions is actually quite powerful. The reason why that fits in also very well in a cloud native is that it scales well with the cluster. It's distributed, it's automated, and it provides a lot of these functions, not all of them, but a lot of these functions, as opposed to sort of monolithic reverse proxies that would run outside the cluster, or maybe even inside the cluster like Nginx or HA proxy. So in my view, an architecture that provides a mesh of services as a service fabric is actually much superior and better way to go, as opposed to having standalone functions for these that are monolithic and that reside oftentimes outside the cluster. Did that answer your question, Mark?
Yeah, it did, although it sparked another one, so I'm going to jump straight in since we still have a little bit of time left over. So a long time ago, I was a continuous delivery consultant, and what we focused on, and I think well, let me flip the question around.
Yeah.
A lot of the time now, the conversation, and I understand why, is about how do things work. But Dan, I believe, Dan Lamotte alluded to this earlier, is that now we will have, and also maybe including Swana's question, now we have perhaps load balancers on-prem, we have them in GCP, we have new updates of our own software, we have new updates of Linkerd and other things coming through. Yeah. From a software delivery point of view, are there any best practices you see emerging? Because clearly, I mean, the benefits are clear, but it also brings this extra complexity on an orchestration level of how do we keep new versions of things moving through to keep this whole stack running. Do you have any experiences there that you can talk to, or perhaps any guidelines, best practices, or warning signs?
Sure. Yes. I do, Mark. I don't think fundamental principles have changed, right? I think test before you deploy, right? But
okay. Yeah.
But having said that, right? So what I see is that, based on a lot of the customers that I work with, some of whom have applications in production, even as we speak. So almost all of them follow a few sort of principles that make a lot of sense, that used to that sort of evolved with time. So chief amongst them is that you almost always have to have multiple clusters, some for development, some for testing, and some for production. You always stage it in such a way that you first test it out, perhaps in development, then in integration, unit testing, then you move it to production. And you also automate the heck out of it, right? We've all been there. We've all been bitten by just that single typo that we did that just brought the cluster crashing down. So the good news is that a lot of the new cloud native clustering techniques is about automation. So automation provides sort of repeatable way to do this. And the third one I would say is that you almost always want, even if you have tested it in your integration cluster, you want to do some type of a canary even in your production cluster. I've seen cases where everything works great in the integration, but then you roll it into production full blast, and then it starts failing. So you want to do a bit of canary. So a lot of these, again, were done with bits and pieces of homegrown scripting and tools, so on in the past. Again, the good news is a lot of these capabilities are built into native clustering technologies these days. So it makes things repeatable. It makes it easier from an infrastructure point of view to roll these out. So these definitely are some trends that I'm seeing. If I look back past 7 or 8 years to how things were done back then to how they are done right now, I definitely see these in the cloud native clustering that people are deploying right now.
Thanks, Ranga. We have one more question before we wrap up. As a follow-up to Dan's original question, I'll remind you, it was how do most companies do rolling updates of their load balancers at scale? He said, could you expound on the second solution? He didn't quite follow.
Sure. So the first solution is based on DNS. Then there were sort of two variants of the second and third solution, both of which were about, I have a set of IP addresses sitting in one instance of my load balancer, and I want to upgrade this load balancer. So I want to move these IP addresses to another instance of my load balancer so that I can upgrade instance one. The two ways you can move IP addresses around in load balancers. One way is you mirror every TCP session from load balancer 1 to load balancer 2. So when you simply move the IP, then all the sessions are available in load balancer 2. All the existing users are preserved, and traffic continues to run. It doesn't really matter if load balancer 1 goes down, you can upgrade it. And then once it comes back up, mirror the TCP sessions and move all the IPs around. You only have to do this if your sessions last for a long time. And fortunately, in real world, less than 1% of applications actually have this requirement. Some examples of these are things like backup or other, I've seen some of these in financials where they have a trading company that opens a connection to a large broker and it remains there for weeks, months, maybe. But most real life applications, 99% of them do not have long running sessions. Their TCP sessions are measured in tens of seconds. And even if you drop a TCP sessions, no big deal because they will simply retry the request. That's what most browsers and apps do, and it's built into the client stack. So assuming that is the case, then the upgrade becomes a lot simpler. What you do is you still move the VIPs around from your load balancer 1 to load balancer 2. Then all the new connections will be handled by load balancer 2. All the existing connections will be handled by load balancer 1. But load balancer 1 is not accepting any new connections. And you wait for the existing connections to drain, wait for a period like say 30 seconds, 60 seconds, maybe even 5 minutes. So now load balancer 1 has dropped all existing connections and it's empty. So you go ahead and upgrade it. Load balancer 2 is handling all the new connections. Once load balancer 1 comes up, the opposite happens. The load balancer 1, which just got upgraded, handles all the new connections. Wait until existing connections drain from load balancer 2. You can go ahead and upgrade load balancer. So these are a couple of different ways you can actually move IPs around without having to fiddle with the DNS.
Dan has one follow-up question there, which is, are there any open source software projects that help you to do that mirroring, to automate that process that you're talking about right now?
Mirroring, not that I'm aware of. Actually, moving IPs around, you can do that with some scripting of your own. It is not built into most open source components, but you'd have to do some work on your own to be able to do this.
Thanks, Ranga. So Dan, Ariel, and Swana, I hope that all your questions were answered. If not, I would encourage you, if you're not already a member of the CNCF Slack, to join up, and you can catch Ranga there, or on Twitter, or the email that you see down at the bottom. All that's left for me to do is say two things. One, I'm dropping a link into the chat right now. That's the link to the next CNCF webinar that we're going to do, which is going to be about an introduction to cloud native storage, something we've been working on for months. So I hope that someone's going to turn up. And second, of course, is to say, Ranga, thank you so much for your time today, for putting these slides together and explaining something about cloud native traffic to us.
Thanks for giving me an opportunity, and thanks everyone for attending it. Appreciate it.
Thanks, Ranga. Bye-bye.